Hello, everybody. Welcome, everybody, to the Machine Learning Meetup Online. Today, we're going to have a special guest. We've got Jules Salzinger, all the way from Taipei, Taiwan, and he will teach us about generative adversarial networks. Now, he will talk more about that in detail in a second. But in case you never heard about them, you maybe heard about deepfakes, maybe you heard about self-driving cars, all of those exciting things with neural networks he will present us today. Um, Before we start, we have some news. I'm together not only with Jules Salziga. Could you say hi, Jules, to the people?
Yeah, hello everyone. Nice to meet you, I guess.
And I'm also with Bogdan Andrusiak, co-organizer from the Machine Learning Meetup Graz.
Yeah, hello everyone. I am also here hiding in a corner of the screen, but I'm here. And before we get to this interesting talk, I want to remind you that we are doing data science course. And just after this talk, we will have our Q&A sessions for people who are working on a project. And if you never heard about our course, you should stay and learn more. And just to remind that the deadline for the final project, if you want to participate in competition, is this Sunday. But you can still finish course till the end of May. So if you just heard about this course, stay for Q&A. We can tell you more about it during that session.
And before we start, we're gonna have a Q&A session with Jules at the end. So if you have any questions during the talk, we're gonna use ahaslides.com/gan where you can put your questions. I put it now in the chat. That is ahaslides.com/gan, where you can ask questions during the talk. So if you have any questions, put them there. And at the end, we will have maybe 5, maybe max 10, depends on how many questions we have to answer for you guys. So that's it. Jules, the stage is yours.
All right. Well, thank you for the small introduction, and thank you for hosting the event, I guess. I'm quite honored to be here. I think those kind of events are really a nice thing for the deep learning and machine learning community. So I'm really glad I can participate for some of this. And today we will be talking about some generative adversarial networks, as Adrian just let you know. So let me hop over to the slides. There we go. Okay, so generative adversarial networks. What a big topic we have to cover today. Since it is that a big topic, we need to narrow down our field, right? So since it is my first talk for machine learning Graz, I have decided to only cover the very basic stuff. We will just do a small introduction today. So if you have more advanced questions, do not hesitate to ask them later. Uh, as for the prerequisites for this talk, I don't think you need to know anything besides just classical deep learning, dense layers, all those kind of things, gradient backpropagation algorithm, all standards. So now let us start. What is a generative adversarial network? Well, first, it is a pretty long name. So maybe we could call them what everyone called them, which is GANs. So what are GANs? GANs, as I said, is a neural network. And more specifically, it is a neural network that solves a very particular kind of problem, which is the generation problem. So in two words, generation is when you have a data set, any kind of data set, And then from this data set, you would like to be able to generate some samples which would belong to this data set. So that's it. We've got what our GANs are meant to do. So what I would like you to get from this talk would be first how GANs work and how they are constituted. And secondly, what are the big problems about GANs? Because, yeah, GANs are pretty tricky to train. You know those guys who told us that video games make people violent? Well, that's because they didn't know about GAN trainings, basically. So we have a lot to cover. So first, what I would like to talk about is, as a kind of introduction, a little bit of a dive inside what the generation problem is and why it is important. So let us consider a data set, very standard data set. So let's imagine that we have pictures of cats and dogs, and those are our samples. And then associated to each picture, we would have a class or a label, which would be either cat or dog. So we can represent this data set as a joint distribution, the joint distribution of X, the samples or the pictures, and Y, the labels, that in that situation, cat or dog. By the way, if you're not familiar with this way of representing data sets and with thinking in terms of probabilities, I strongly advise you to consider learning about that, because it is very useful to get an insight into some kinds of deep learning methods. So if we want to know the whole data set, what we would like to know is actually the joint distribution, so that distribution over there. But what we usually do is something a little bit more simple, because this would be too hard. So what we usually do is, for example, classification. Classification is a very common problem. And in the case of classification, what we would have is this. So from our data set, we would get our picture here. And from this picture, we would try to guess the label. So in that case, we try to determine the marginal distribution of the label Y given the sample X. Now, I'm sure you all know this formula here, but this tells us that actually when we have a good classifier which determines this, then we are this term away from knowing our whole joint distribution, which would encompass everything we need to know about the data. Let's look a little bit more into this term here. So basically, P of X, what does that mean? Actually, it's pretty straightforward, right? It's for any given picture in the state of all possible pictures, what would be the probability of this picture belonging to the data? And actually, this is exactly what we want to determine inside the generation problem. So the generation problem will be how to determine what kind of sample belongs to this. Actually, there is a slight modification that we sometimes encounter in the generation literature, and it is this problem here. So this problem where you give yourself a label and you try to generate a sample which corresponds to this label. So instead of saying inside my data set with cats and dogs, I want to generate random images, you would say inside my data set, I would like to have random dogs specifically. In our case, and in the case of what I will call the vanilla GAN, or its most basic formulation, we will only consider P of X, but there are GANs that work very well and arguably even work better that can solve the P of X knowing Y problem. So what does this all say? Because usually when you open this kind of talk, you talk about some application, and in a way, I'm talking about why this problem is useful. So this is kind of an approach to applications. But why do I put it this way? Well, let me tell you a little story. there is a legend that says that if you want to be a deep learning in NVIDIA, in an interview, they will probably ask you this question: what can you not do with a GAN? And as the story says, the expected answer is nothing. There is nothing you cannot do with a GAN. So this was a little bit of a mathematical approach to give you a feeling of how this kind of problem, the generation problem, can be theoretically useful in a lot of way. Where to give you a precise example, that would be the case of semi-supervised learning, where you would perform some kind of data augmentation. Data augmentation is often very useful, but it makes use of some known your data set. And in that case, you don't need that because you know the probability distribution of X. Therefore, the only thing you need to do to augment your data set would be to create new samples with the generator. Now, of course, this would assume that the generator is perfect. And in practice, this is not the case. So in practice, we must be a little bit careful with procedures, but you get the idea. So now that we all agree that solving the generation problem should be useful, uh, how do we solve it? Well, using a GAN. And before talking about GANs, I would like to use a little bit of a metaphor, which is very well known, so that you get basic idea that's behind this very specific neural network. So this metaphor is arch forgery. So we will imagine that our original work of art is a tomato. So in our case, this would be a data set. So we would like to generate random tomatoes. Okay, I want random tomatoes. So I will place an order to a very famous counterfeiter. And the role of the counterfeiter will be to generate me a new tomato. Perfect. So let's see the result. As you can see, it is pretty flawless. So there's no way we can tell the difference. It is round, it is red, it is shiny, it is everything we want. So in the face of something so faithful to the reality, how can we determine which is the original and which is the fake? Well, we will need to call upon the help of an expert. And the expert, who is well versed in everything that regards tomatoes, will tell us which one is the real tomato and which one is the fake tomato. Well, this seems a little bit metaphorical because it is a metaphor. So let us link all of that to what really is a neural network. And we will see that this metaphor is accurate because it makes use of two main actors, the counterfeiter and the expert. Therefore, if we go forward to the architecture, we will notice that the GAN is not actually a neural network. I lied. It is actually a couple of two neural networks. The first neural network will, of course, be our generator neural network. The goal of the generator neural network is to act as a counterfeiter and to generate random images that would, we hope, belong to the distribution of the original dataset. Now, if we want the generator to generate random images, we need to give it a random input because, as you may know, neural networks are deterministic in nature. So if we want them to become probabilistic, we need to um, inject some probability somewhere. So this will serve as our input. Usually, we just sample a random Gaussian vector from a normal distribution, and that is enough. Then, of course, we need a data set. Here is our data set. So in that case, beautiful flowers. And we would like the output of the generator to be also a beautiful flower, which at the moment, obviously, it is not. Therefore, we need to get some feedback. And this is where it gets difficult, because how do you know if the sample you just generated has the same properties than the images that are in your dataset? Because having the same properties as something it's a bit vague, right? You cannot tell a computer do something that's approximately like that. It doesn't work like that, right? You need to be precise about it. So in order to generate this precise feedback, we will use the expert, which in our case will be called the discriminator neural network. So the goal of the discriminator neural network will be to take as an input sometimes some images generated from the generator, sometimes some images sampled from the dataset, and every time it gets a picture as its input, it will try to classify whether it is a real image or a generated image. So in that case, now how do we train this? Basically, our discriminator will of course be trained to classify correctly the generated and the real images. That's just like a classification problem, very standard. But how do we? That's where the genius of this idea is. That's also where the nightmare of this idea is. Because basically, the generator will try to generate images such that the discriminator then classifies them as real. Therefore, in order to train our generator network, we will get gradients coming all the way from there into there. And if the images generated are classified as real, it will act as a positive influence on the generator and as a negative influence on the discriminator, because of course the discriminator wants to be correct. Now that is a big problem, because here we are not in presence of something that we could call standard machine learning or even standard deep learning. Why? Because these two networks don't try to go in the same way. They share the same loss function, but they're each pulling in their own direction. So this will be a big problem, because this means that since the generator is part of the discriminator's objective function and vice versa, basically the objective functions are moving during the training time. And this is not an assumption we're used to making when we use gradient backpropagation. Therefore, our usual methods don't really work. And the problem is that we don't have another method. So basically, we'll have to go with what we have and hope for the best. And this will usually not work, except if we have exactly the right hyperparameters. We'll come back on that later. But in order to introduce this problem, I need to talk about another metaphor. I'm sure you love them at this point. So let's talk about a little game. You are an operator, which means you have a problem and you want to solve it. And your problem is that this guy, G, the generator then, is weak. And you want it to become. So that's your goal. That's the only thing you're interested about. Because if if G is strong, then it means it produces nice results. And the problem is that you cannot just tell him, be strong, please, because as we saw on the previous slide, it is too vague for it. So in order to circumvent that, we find him a little buddy, we call him D, and we tell those two to play a game. This game will be the game of the rope. So in the game of the rope, both players pull the hardest they can on the rope in their own direction, and the first who falls loses. And this is pretty similar to what we saw on the previous slide for a GAN. And just as what we saw in the previous slide, we will see that we can conclude very interesting things that will give us great insights into the problem our GAN may face. The first problem will be that actually in this case, you don't care about who wins the game. The winner does not matter, in other words. So what does it mean? Basically, if G wins the game of the rope, it doesn't tell you anything, right? You don't care. You just want G to be strong. And in that case, G could very well be weak and still win because D is even weaker. G could very well be very strong and still lose because D is even stronger. So the main feedback you will be getting from the game, which is the result of the game, doesn't interest you in the slightest. So this is one of the main problems. It is that usually we have a very interesting metric which we can follow in order to see if our method is successful. In that case, the main metric we have access to doesn't work. So we will have to find other things. The other problem is that of imbalance. Imagine that you play the game of the rope between a 10-year-old child and, let's say, a professional bodybuilder. Well, this is kind of an extreme case, but you can easily picture that nothing good can come out of this situation, right? If they're really serious about it, the child might even die, so there's no hope in training in that case. And the professional bodybuilder obviously cannot train facing such a simple problem. So usually it will even grow weaker because of a lack of proper training. Now, of course, we are still in the metaphor here, but this is actually very similar to what we observe inside of a GAN. And this is what we will cover later. Because basically, it might seem okay to imagine that when the generator is really stronger than the discriminator, then it will go wrong. Because if the generator is really smart, it will be able to find little tricks to fool the discriminator very easily. And then it will fool the discriminator with nonsense. And as soon as the discriminator tries to adapt to this nonsense, the generator, being stronger, will adapt even quicker. And you will never converge. But when the discriminator is stronger, it is a little bit more difficult to determine why this would be a problem. Because in theory, the stronger the discriminator and the better, the purer the the signal coming from the discriminator will be for the generator, which in the case of a dynamic game between the generator and the discriminator is very important. The variance in such a setup is very high. So if we can reduce this variance by providing a more confident response from the discriminator, this should be very interesting for us. So why is it not? We will see that later. Before going into this kind of detail, I need to introduce more formally those two players to you, because at the moment, I didn't give you a lot of details. So the equations I will present you on this slide were all made by this guy, Jan Goodfellow, which drafted the original generative adversarial network paper. This was in 2015, and basically at this point, this guy is a god. Okay, so just so we are clear. For the next, I don't know, maybe 5 years, every single research paper on the subject just copy pasted his loss function and you reused exactly the same formulation to explain their procedure. And afterwards, when these loss functions started to be changed, there was actually pretty significant improvements. But that's not what we're here to talk about. So what is this equation? So let's see what the loss function is from the side of the generator. So what does it say? From the point of view of the generator, if it generates a sample, then the discriminator should say it is real. So this is all into this little equation here, which says that when we randomly sample a normal a vector from a normal distribution Z, and we send it inside our G network, then we send a picture inside the D network, then this should be minimized, because remember, this is a loss function, we want to minimize it. Therefore, if the log is minimal, it means that this should be minimal, which means that we want D to say 1. And in that case, 1 means real. So by the way, this here is just the cross entropy loss function. So this means that using the binary cross-entropy loss function, here, what this says is, please discriminator say that it is real. Now, what about the discriminator side? Well, basically, for any generated sample, the discriminator this time should say that it is generated. And from any sample taken from the database, then the discriminator should say that it is real. In other words, if we sample X from the data, so this means we take any sample inside our dataset, then when we send this sample inside our discriminator, it should go towards 1, just like there. This is because when we take the example inside our dataset, it is real. And there, below that, we can see that this is exactly the same equation as in here, except that in this term, there is no 1 minus. Therefore, this doesn't need to go towards 1, but towards 0. In other words, when we use the generator with the, and then we send it to the discriminator, we need that to be generated. All right, so now we have both our players. But where is the game, right? We have our players. Let's see what the game is. Just like with our metaphor, I'm starting by introducing who is playing, and then I'm introducing the game. In our case, the game will be played with a general loss. So how can we make the two different losses into one single loss, which will be the loss of the GAN? Well, if we look at this equation and we take it from the side of the generator, this second term here is exactly the same as the one we saw on the last slide for the generator. So if we minimize this term, we should be all right. What is this term? This term is actually something that's got to do with X and D, but there is no G here. So this term is independent of G. Therefore, when we derive this and send the gradient back into our system, the gradient of this with respect to G will be 0. So if we train G with this equation, it is exactly equivalent to what we saw on the last slide if we try to minimize this. Now, from the point of view of D, now we have something interesting here. We have that this should say that an image from the dataset is 0. And we have that this should say that an image from the generator should say 1. So in other words, it's just the exact same equation than on the last slide, except reversed. So how do we do? Well, there's a trick in math. When you minimize something, you can also maximize the opposite. So in that case, we have the opposite of what we want. So if we maximize this loss, we should be good to go. And in that case, we will have a general formulation which encompasses both of the needs of our two players. So if we follow this equation, this optimization problem, the minimum for G of the maximum for D of this loss, then it should, in theory, lead both our discriminator and our generator towards the right solution. Now, the problem we have set for ourselves is we want G to be strong. So what does this mean with respect to our loss function, which is a mathematical object? That's all great. That can be understood by a computer, but that's not what we want. So why do we use this? Well, of course, the first reason is that we cannot just say to the computer that G should be strong. We already talked about that. But there is another reason. The other reason is that, and it is very properly justified inside the original paper, actually, the optimal solution of this corresponds to a point called the Nash equilibrium. This comes from game theory, where G actually reach the actual distribution of the dataset, and D gives then a random output because it cannot do anything better since the distributions are the same. So it has no other recourse than just answering randomly. So that is very interesting and actually pretty ironic because we set for ourselves a loss function which has maybe it's a little bit related with what we want, but it's not really what we want. And if we reach this loss function until the end, then actually this guy will not succeed to what he initially wanted to do because half of the time the discriminator will have a correct prediction. And this guy will also fail at what he wanted to do because half of the time he will get a bad prediction. So none of those two players won their game, but you, the operator, won your game because you had what you wanted. G is strong. Therefore, we can prove that if we use this loss function, which at first doesn't seem like it's interesting to us, well, if we carry it out until the very end, something that's interesting. The problem is that in practice, we are not sure that we will reach this optimal point. So the question would be, when we haven't reached the optimal point, is the solution found by this close to the solution we want? In other words, is the mapping between our expectation and the expectation of our players smooth or not? And I have no answer to that. In general, from what we can see from the research that's been done, sometimes it works, sometimes it doesn't, and most of the time it is very, very irritating. So now let us talk about the problems of GANs, and there are a lot. So this is an equilibrist. May I present him to you? That's you, actually, training a GAN. Because one of the main hyperparameters you will have to influence the training will be the learning rates. And the learning rates directly controls the speed at which a network can train. Therefore, since I said that you had to balance your two networks, this will be your main tool in order to define a dynamic system which will converge to what you want. So here is a first case. If the generator is too fast, we already talked about that. It will just give garbage to the discriminator and fool it with this garbage. And as soon as the discriminator catches up, or even starts to catch up, the generator will adapt. And this will create a cycle. So instead of of converging towards a stable point, what might happen is that you will reach a metastable a metastable point where um, the solution to your equation basically circles around, and it's basically a game between a cat and a mouse, and it never converges to what you want. So this is the case where the generator would be too fast. Now, what if the discriminator is too fast? Well, as we already said, you lose as well, but it's a little bit more difficult to know why. I will cover this topic on the very next slide. And last of all, what if they learn at the same speed? Well, even in that case, I'm sorry to tell you, but this might very well be a failure again. Why? Because of course our very dear back gradient backpropagation method. Well, sometimes it works, sometimes it has a little bit of trouble because the search space is so huge. And usually the loss function is a bit tricky as well, you know, with all those local optimums and those kind of things as usual, but in that case, it will just add up to all the problems we had. So there could be a lot of problems that happen even if both your networks are at the same speed. But there is one in particular that's especially problematic and that we will cover as well on the next slide. So let us see. The first problem I want to talk about is the problem of the disappearing gradients. Now, those of you who studied deep learning, you might be very familiar with this because it was a huge problem for picture and image classification back before 2016 when ResNet came to save the day. And the problem was that at this time, the most commonly used activation function for our neurons was some kind of sigmoid function. And these functions tend to saturate when a network becomes too confident. Because usually a network gaining confidence means that since our labels will be one-hot vectors, they will contain ones and zeros. So the output of this should be all the way there or all the way there. And when they are, the gradient is very, very small. In general, this may not be a problem in every case. But when you stack layers upon layers upon layers of these kind of things, moreover, I didn't talk about that, but don't forget that usually, thanks to your great acidity principle, you want your weight to be quite low as well. That's why you usually regularize your networks with two loss, for example. And so if you want your weights if you want your weight to be low, then you will multiply each time you backpropagate through a layer by a small element that will usually be lower than one. Therefore, your gradient will lose a lot of strength if you backpropagate it through a lot of layers. And the more confident those layers will be in what they are currently analyzing, the more gradient will be lost. Therefore, you will very soon find yourself in this situation where you will anxiously follow the metrics that come on your screen and trying to determine if the norm of your gradient is correct. And when it does, well, you lose because the gradients is what the generator needs to be trained. And since the discriminator and the generator are fighting against each other, we cannot rely on the usual fact that when we converge and the norm drops, then it means that we are done. Because in that case, it doesn't mean that we are done. It means that the discriminator is done, but it doesn't mean that your generator is all right. So if we summarize all this, this is my little GAN picture here. When the information goes that way and the gradient goes that way, the more our discriminator is confident and the less the generator can learn. So if by this time the generator is already pretty good, but in the generate case, if the discriminator is too strong, then the generator will not have time to follow. And even though the quality of these gradients will be higher and higher, and the training will become more stable, it will also mean that the generator does not have time to follow the discriminator. So this is why we need balance. Even when we have balance, as I mentioned, this is not always a happy life for the operator because we could face these kind of problems, the mode collapse problems. So in order to explain mode collapse, the best way is to use this kind of distribution. So this is what is called a bimodal distribution, where we have basically two modes. So this one for -2 and this one for 1.5 approximately. So this will happen when you have a distribution where two cases are possible. For example, inside our first data set, we had pictures of dogs and pictures of cats. So if you want to represent all these pictures into one single dimension and you find out the probability density of this, you might find something that's a little bit difficult to determine if it's a cat or a dog. And you will have really the doggy dogs and really catty cats. And what is a mode collapse problem? Pictures of numbers between 1 and 9. And here, what this generator tells you is basically that in order to count from 0 to 9, well, you basically go 1, 8, and you're done. So this is not exactly what we should have, but there is a problem here. The problem is that those 1s and those 8s are actually very realistic. So in a way, the generator kind of fooled you because he did what you asked. He is now very realistic, but this is only for the marginal lows. So if we give him the order to create a 1, it will be very strong. If we give it the order to create an 8, it will be very strong. But in our case, I only showed you how to make generators that can copy a whole data. And this is not the distribution of MNIST. So we failed. And how can we solve these kind of problems? Well, for the disappearing gradient problems, we usually use some tricks in order to make sure that the discriminator doesn't get too confident too quickly. For example, you could add noise to the outputs um, of your discriminator in order to make sure that sometimes he will think that he's wrong where he is not. And in that case, the discriminator would have more trouble learning. But in case of the mode collapse problems, it's a bit more difficult. Sometimes you could just add a few layers to your generator or add some width in the hope that the problem came from the fact that your generator wasn't powerful enough and didn't have enough expressivity. But that will not solve the problem all the time. So I hope that with this, I have really helped you get a feel for how difficult it was to be a GAN engineer in 2015. Hopefully, we are not in 2015. We are in 2020, and in this day and age, there is a lot of research on these kind of things. So, in only 5 years, I can already tell you that there has been a tremendous amount of progress. But this is not what we have time to talk about today. And actually, what we had time to talk about has come to an end. So I hope that you all liked this presentation. And I would like to thank you all for your attention if you're still here with me. If you have any question, I would be very happy to answer them, even if we don't have the time to cover them today. So here is my email address once again. I love answering questions. Do not hesitate to use it. Before ending, I want to add that I will actually be coming to Graz for work starting this summer. I will be working for Reactive Reality there. So if you're not familiar with what they're doing, you can always visit their websites. And they also want me to mention that they are still recruiting. So if you're looking for a job, you can contact this guy here, and he will probably be very happy to answer you as well. Now, this concludes everything I had to say. So I give it back to you, Edwin.
Thank you, Jules. Thank you for this amazing presentation. So, if you want to ask your questions now and if you want to answer us now, you go. I put the link on the chat. So let me now go to the oopsie. Let's 1 second. Let's put the questions on the screen. Now, in a second now. So I think now it should be working. Yes. Technical issues always. So we've got already a question. We've got a question from a scene. Thank you for your talk. What kind of real life industry problems are adapted for this model?
All right. So, well, first, no problem. It was really my pleasure. So, what kind of real life industry problems are adapted for this model? There are a few. I'm not sure if you would qualify them of industry kind of problems, but in theory, it could be adapted to industry. Let me develop a little bit. So basically, um, At the moment, GANs are mostly limited to the research domain, but this is mainly because it was too unstable until now. Nowadays, with the GANs becoming more and more stable, they also become able to be applied to other problems, as I mentioned in the beginning of my talk. For example, helping classification tasks with a very little amount of data to train stronger classifiers with data augmentation. Especially modern works have really been able to capture the data distribution from a very limited amount of images. And that way, they could, with a very, very small data set, uh, infer what the distribution could be. So, with this kind of tool available to us, it would be very interesting to adapt GANs in order to use them for almost every kind of other problems you could imagine. But if you talk about industry related problems where generation would be used for the sake of generation, so where generation would be the objective, then you would have two kinds of application, or at least two kinds that I can think of right now, which would be for the first suited algorithms to generate fake news. Then studying GANs can allow us to fight this generation. And especially modern GANs have known a lot of focus on that lately. Because when the generator becomes, in a few words, if you make your generator become a smooth function, you can invert it. And when you invert it, you can retrieve whether this generator was used to generate this fake or not. So it can be pretty useful. And the second case would be in all cases where you would need to have very realistic content. So it would be in general customer service or anything like this, where you would want to generate a very realistic image from either a very noisy content or no content at all. So we could imagine, for example, some filters, some interesting photo filters, which would turn something that's not beautiful into something that's beautiful by human standards. So those are possibilities.
Hope that answered your question, Masin. That was a very, very deep answer for for such a question. Next question we've got now from Anonymous. He asked, "What are the limitations of GANs?"
All right. So in theory, there are none because well, if you, it depends from which point of view you take this question. Actually, if you take from the point of view of which data, which probability distribution can it not model, well, usually, correct me if I'm wrong in the chat, because my math doesn't go as far as that. But if I remember well, data distributions are Lebesgue integrable. And we have a theorem in deep learning which states that if you use certain kinds of activation functions, then we can prove that using enough nodes, this is the extended universal approximation theorem, then you will be able to model any Lebesgue integrable function. So in theory, nothing stops us. Of course, in that case, what will stop us is in practice, because as I said, the actual learning problem is very difficult to solve because the optimization problem is not adapted to our optimization solver. So we will most of the time be limited by this kind of things. And what is the limit of this? I cannot really answer, because if I had answered 3 years ago, and if I had answered 2 years ago, and if I had answered 1 year ago, I would have answered totally different things because the thing evolves so quickly. What was impossible yesterday is now totally within our reach with the amount of research there is. So really, in theory, there's none, but we will see.
So now we've got another question from Anonymous again. maybe the same anonymous, maybe a different one. Who knows? Is there a commonly accepted opinion on whether the deviation in humanly generated content is also coming from randomness?
All right. Can you repeat the question again, please?
So, is there a commonly accepted opinion on whether the deviation in humanly generated content is also coming from randomness? So,
Whoa, this is a
yeah.
very
So
philosophical question.
that's a very philosophical question regarding that. Yes.
Okay, so in this kind of situation, I could give you my personal opinion, but you're asking for a generally accepted stance, which I must say, not being my domain, I cannot provide you. So I don't think I'm able to answer your question truthfully. Sorry.
Okay, we're gonna answer one more question before we go, and that is, can you compare GANs to variational autoencoders?
Yes, we can compare against with variational autoencoders because they basically solve the same problem. Now, we want to go into the theory of what makes both of them different. This is math that I cannot handle at my level. So, if what you ask me is what is the theoretical difference between the two, I cannot say. However, what I can say is that both of them have had pretty good results at first, but after some amount of research, GANs kind of left variational autoencoders behind because way they converged, they had better results. So in theory, I couldn't tell you. In practice, the GANs are definitely the winners. However, in some cases, you might want to use variational autoencoders, especially if you want to use some interesting tricks, such as having more control over your latent space. So the latent space is the central part of the network in an autoencoder, just after the encoder and just before the decoder. This is the latent space. In a GAN, the latent space is actually the input of the generator. So since it is an input in the GAN, well, there are some ways in which we can influence that, but not a lot. Where in the case of a variational autoencoder, this is actually the result of a first encoder. So we can regularize the first part of the encoder in order to ensure that we have certain properties for our latent space. And this is why sometimes it could still be possible to use variational autoencoders, but honestly, with recent GAN works, especially if you're interested, you can check out Style GAN. These kind of things will actually add these encoder parts so that they can tweak the properties and especially the topological properties of their latent space. Okay, that's it.
Yeah, and I mean there are a lot of things about variational autoencoders we could go way deeper, especially now with the latest research from DeepMind with this VQ variational autoencoder 2, where they had comparative results with Big GAN. But this is out of the scope for today. Well, before we go, I would like to give a quick shout out to our sponsors. So, interesting enough, you mentioned reactive reality. So they provide pizzas for our event. Now, the thing is, we cannot offer you pizza now, so hope you enjoy your virtual pizza. Enjoy your virtual pizza, and also no cent we're on to before providing the room of the event and drinks. Again, there's no room now and there's no drinks, so please enjoy your virtual drinks also with us. So that's it. Jules, thank you again for coming to us, showing your knowledge, and really giving us intuitive explanation of how generative adversarial networks work. And that's it. Thank you again. And I wish you then a great day. And regarding that, until before we go, one thing to mention is we are going to have now the Q&A session for the assignment for the data science at course. So if you're struggling with the assignment, it's going to start anytime soon. which is going to go to 5-minute breaks. So until then, I want to say one more time, thank you, Jules, and hopefully we'll see us when you're here in Graz at the meetup, and we can also talk face to face more about GANS in the future.
I hope so. Thank you as well. And it was really my pleasure. So, goodbye.
Goodbye.